Hi, TechRabbit here. Now I'm going to continue a little bit more of this AMOS Basic Pro archaeology. So we're going to have a look at the entry point logic and analyze it a bit. So it's like going even deeper down the rabbit hole that we already started. I've added some additional information in the comments section of the video, so if you want to catch up on what we've gone through in previous episodes, then you can actually get the links there easily. So I added about the a link to a video about the editor that I'm using and the setup for that, and also about the compiler and the usage of, and also about the Amiga emulator, and also the basic setup of the AMOS Basic Pro. So let's get started. So just a little bit of background information I think would be useful to repeat for this video. The original source is 100% Motorola 64K assembler, and the code is specific to Amiga OS 2.04. Then the code, it seems to be somewhere that it started around 1988, and then the last date entry I could find was 1992. So that's the span of the development period. And over the time they were doing this development, they seem to have used two different versions of the HiSoft DevPac compiler. So the first version was GNOME 2.14, and that's copyrighted 1985 to 88. And then they moved on to using GNOME 3.02, which is from 1985 to 92. So what makes this interesting with this background is this is the golden age of hardcore assembler programmers. So it was made in the height of the of basically assembler programming on the Amiga, and you did have the parallel development with which you could write all code in C, but most professionals considered it like you weren't writing real programming code if you didn't use assemblers. So this is still hardcore assembly, which makes it extra interesting for those that are interested in this type of low-level code. So anyway, just one side comment. The original include files in the original project, they were for release 1.3 from Amiga, and they only included the include files for assembler. So to make the documentation a little bit more complete, I've actually yeah, and then they only used a subset of the include files also. So what I've done now is I take the full set of include files, both the assembler and the C files, into the project that I created, and they are from 2.04. So I found that to be a bit more logical. It's so relatively low-level code, so I think that I would assume that they didn't use any features that were specific to 2.04. So they just yeah. So it would, if there were any changes that were 2.04 specific, then they hard-coded it. They hard-coded values in the original assembler. So I've tried to actually swap out where they've hard-coded things like struct property offset values. So I've changed it to a name, and yeah, another small cleanup so to make it a bit easier to understand the code. So as usual, I'll be including this this specific project in my GitHub repository, so that you can actually download and compile it and investigate it yourself also. So anyway, let's get started. So they've used there a little bit of an odd naming convention, but the +b.s file is the main program file, and then it's also the entry point into AMOS. So what they do is that they've created sections, and they call it section E is the first section, and they called it hunk 1, and or gave it a label hunk 1, and a bit of odd things that they put, like it says end routines first, and then they basically when the Amiga loads this, then it starts executing from here, and then it hits this one, and then it jumps to something called cold start. So it jumps over this section, which actually has the end routines. So now we're in the cold start section, and this is hunk 2 label, and the cold start label. And also I've included, in some places I've included this line entry here, and that's the reference to the original source code file, because this +b.s only contains the code that we're analyzing right now, and everything else has been removed. So what does it do after it comes to the cold start section? The first thing it does is it saves the stack pointer into save SP, and then it makes a reservation for a stack buffer. So basically what it's going to do is, it's in the address space reserved for the stack, it's going to actually put its own working variables. And then also it saves the because the Amiga OS will pass the information about the command line and the length of the command line in the command line address will be in register A0, and the length will be in D0, and then this just moves it into this stack pointer data section SP command. So I just wanted to show you the definition of the stack pointer data entries, and then here you have in this section buffer into the stack to start. You have different parameters, and many of them are used. So now Amiga has a convention where the exec base for the library exec is stored, is a hard-coded value, is a specific memory location. And in the original code they did a lot of this, because they were hardcore assembler programmers that have been doing Amiga programming for years. They knew exactly what these addresses are, so they like, here's the original code, so they put move L, and then they say, oh, it's 4, and then it's a word, and then we store it in there. So what I've done is, in the case where they've been using hard-coded values that don't mean anything to a modern person, or makes it very hard to understand, I've actually used constant. So in this case it takes a constant absolute exec base and then stores it in the stack buffer. And this makes the code a lot more easier to understand, because you don't get you don't have this like hard-coded $4 all over the place, and you don't know if it is the exec base that they are talking about at that specific point in the code, or is it some other number 4 value. So basically on Amiga, to get started you need to open a bunch of libraries, and usually you do that by providing a name and a version, and in this case they ignore the version. And so here you're putting the immediate address for the name of the DOS library, and then after that it sets up the execution base, and then the version that it was going to use, which is 0, which is it doesn't care about it. And then it calls the open library, and then when it gets the value returned, which is the library reference, then it just stores it into DOS space, into the variable DOS space to use. Also, one of the things that in the good old days, there was everybody knew how to do Amiga programming in assembly in their sleep, so there was absolutely no need to have any documentation in the code for how things are set up and used. So what I've done now is I've actually inserted the documentation for the library calls, so you can actually very easily see, like, what is the library name, what's the description, what's the C declaration, can be useful if you want to actually implement this in C, and then the register usage, and any other, and then also a URL to the online documentation. It makes it a little bit easier to understand. Makes the code longer, but taking into account this 35 years later, very difficult for people to understand how the code works if it's not inline document. So moving on, and I also added some examples of adding diagnostic messages. In this case, this is will tell you where it is and what has happened. And so here it's program started and DOS library opened. So here, and also this stores the registry values and then restores them to the original state. So you don't have to be worried about the fact that, oh, did you use a register that is actually used by the program and you're going to screw up something. So anyway, this sets up DOS space, gets the output handle, and uses the output handle, sets this, and then it sets up the write function. And then this message here is just this text that you have up here, and then you have the length also for the length of the message. So it's not a zero terminated string. And also the same thing that I've copy pasted the reference manual information, and with the link to the online reference, so it's easy to find. And then it just jumps to the system subroutine and writes out the text. So okay, now it's going to open basically Amiga has, well, it's got a pile of libraries, but the main one you usually always start with is the DOS library, what they call the Amiga DOS library, and then the next most commonly used library is Intuition. So here it's opening up the Intuition, so it sets up the execution base, which is the reference for all system exec system calls, and then it's again sets up the version and the name for the library. And then it calls open library, and then it stores the reference result. So now we got two libraries open, so the DOS and Intuition. And then here it's going to just clear all the stack variables, so to a non-state. And then the next thing it's going to do is it's going to try and find out if, because in Amiga OS it makes a difference if you start the program from the command line, from the command prompt, or if you start it from the actual graphical user interface, which is called the workbench. So there are certain processes that only work if you run it from the command line versus the workbench. And the way that what it does is that it's going to go and use find task to find this task that has been started. And then in the task you actually have a pointer to the command line interface if it has been started from the command line. So it calls find task, and then it has a look at it, and it tested if this here I forgot how this worked actually. Okay. What was A0 then? A0 gets blanked out. So D0 is the task that it gets returned, and then it puts it into A0, which is the reference to the struct for the task, and then it uses this as the struct internal offset to actually get the value for this variable. And then if it's not equal, then it jumps to from CLI. So it doesn't actually use the command. Yeah, it doesn't actually use the command line interface reference for anything. So anyway, so now it jumps to from CLI, and I just put in a diagnostic message here so we can see that it actually did start from the CLI, so that will be printed into the terminal. And then it goes and retrieves the SP command data, which was the address and length of the command line. And if there are no command parameters to process them, we just go directly to command X. So I just have a diagnostic message print out that the command line parameters found, if there are actually command line parameters. And the first thing it does is that it now terminates the command line. And I've actually described how it actually does that, so basically what the logic behind this here is. And then when it comes to the command line, then I've tried to investigate and reverse engineer what format or what types of command lines are supported and what can lead to an error. And so I found these combinations are valid command lines, and even the one that doesn't have any command line parameters. And then you have this one here you can enter if you want to generate an error condition. And there's a logic that it uses to parse the command line and break the command line into different parts. And the key here is that it'll skip over spaces, and then it knows how to handle options, and then it will actually store substrings. It will extract substrings and store them in different stack variables. So we'll just have a real quick look at this, because I'm actually going to make another video where we look at more into detail into this parsing mechanism. So we have a subroutine embedded in the command line handling to actually extract a string out of the command line. Let's see. So for example, this string here is extracted, and then that string there is extracted. As I said, I'll be coming back to that in a follow-up video. So if it determines that it's started from the workbench, then you actually don't get a command line as such. So there is no command line. So what actually happens is that the Amiga OS will send a message to your application, and you need to actually go pick up that message. And if you don't, then Amiga OS gets upset and throws an error. So it's very important to retrieve the OS messages for the application. So I just put it in here, where you go and get the where did I put it? Yeah, you need to get the message port for the application, and that you can pull from the task. And then you wait for the port to activate, and then you go get the message, and then you change to the directory, because it has an argument list that has the name and then the lock information, and if it's not locked you should lock it. So that's how I tried to explain it here, step by step. Here, set up the lock on the startup target. The Amiga OS has this feature that if you're gonna, when the application starts and it opens a file, then or it's going to use a file, then it needs to apply an application lock on it. And if you have more than one message, then it means that the second message will contain the name of the file to load. So I'll demonstrate it when we get to the UI, but you can have it. You can say that you start up the AMOS Pro, and then associated with that you make a reference to an AMOS file to load. So then you will get two messages, one for the base application, and then another one that will contain the message which indicates the file to open. So I've added actually a diagnostic message here. The program started with two arguments. And let's see. So what I did now is I inserted because you don't have a command prompt to throw text to. So then I actually added I created a diagnostic message based on an outer requester, which is like a lightweight window that you can pop up to display the text. So in this case, it's reporting that the program has been started with two arguments, which is actually faced, I should say, two messages, really. Two arguments. And I will just display the text, so here you can see. And this was a bit of a complicated setup, so what I've tried to do is I've tried to, again here, without going too much in the details in this video, but I've broken down all the properties and documented them and tried to be very clear on what's what. And then I've actually added the again documentation about it and references to the online documentation of what is this actually trying to, what is it talking about, and what is it handling in terms of data. Because the original code was just that it had an entry to create an outer requester, and with absolutely no additional information. So you had no idea what it was. Like, for example, this one, I mean, what's that? Like, or what's that? Like, so I tried to document it very, extract from various document sections into here, so that you can very easily see what's happening. And also, again, documenting, showing the call structure and then the registry usage, so you can actually see what data is being provided. So here it's picking up the argument list, and then it's going to get the WA lock from the second message. And this was also hard-coded, so I tried to really explain this and also remove the hard-coded like it had hard-coded struct sizes and stuff, so I tried to get rid of all that. So there's nothing, everything is constant based. So here we go, copy the second WA name to SP auto name. So that the SP auto name is the application to start. So the .amos file to and I'll try to put in a requester to actually show the auto name. So, and then we come to the end of the basic workbench processing, and then it will jump to Command X. Command X is kind of like the, if everything succeeded both from the workbench perspective and the CLI perspective, then it ends up, or then it just calls Command X, and Command X is the endpoint where it starts the processing of the rest of the top level logic for to start the AMOS processor. And then it actually does have some error handling, so I will show that. So if things go horribly wrong, like a command line can't be parsed correctly, then it ends up in this error with unreserved data zone section. And since I haven't reserved any data zones, then this doesn't, the data zone reservation thing is not really particularly interesting. But and then I also put in a diagnostic message here. It's just saying that it's going to unload segments. And then it will close the libraries. And it will display a message, and then it will go to get out. Also reserved some diagnostic messages. I put a comment here that they won't be, they basically can't be reached as it is now, but then you can actually move this around to other sections as we add more code at a later date. So here, and then here it's getting out. So it restores the stack pointer. It displays a message if there is one that has been provided. And this forbids task rescheduling. And here you have the very important reply message. And then it gets out. Yeah, a message provided means that it was this, because this all handles both cases, that it's the program as being called from the command line or from the workbench. So in the case of having if it was called from the command line, then it just jumps over this forbid task rescheduling and reply message section, and then it just exits. So here it gives the return code and then RTS, and then it returns to the Amiga. So anyway, now that we've gone through that was the level of detail I thought I'd go through it. And as I said, I'll put this up in GitHub with a reference in the comments so you can find it. And I just thought I'd demo a few use cases. So anyway, I thought I'd just demo the command line first, or the shell first. So look at what happens now when we do this. So when it's compiled, it's put into the out directory, and then I just basically using the out directory as a drive in the emulator. So now we see all the whole sequence. And then it also I have these diagnostic menus, so you can actually see from what place to exit. So here we can see the program started with DOS library open, program started with CLI command line parameters found. And then it extracts the config file name. And then it says the /w is workbench requested, and then name is the program to start, the AMOS program to start, which is the program to run, and then it exits. So you can actually very easily now you can look at the source code, and then you can actually run it, and then you can see how it actually works through the process. And then if we make an error, see what happens, and then we see that it ends up in the error path, and then you get the bad command line as a result. And then we will try the workbench. So here I just set up very simply, I set up the AMOS Pro icon, so this stops the program directly. And then as you see that it goes in, it does the workbench processing, and then it just goes to Command X, and then I have a requester, or a simple requester that just says that it's in the Command X section. And then to get it to get more than one message, then you have to select, so that's Shift, and then you select both, and then you double click on AMOS Pro and still keep the Shift down, and then you see now you get this program started with 2 arguments, and then here it picks up the name of the other file, and then it ends up in Command X. So that took me a while to understand exactly what the sequence was for Amiga to do this. That's the way you get the dual message scenario to work. And then actually if you select more than one icon, then you'll get more messages. So you could potentially open I actually don't know. I didn't actually look if it supports more than one. If you tried to open more than one AMOS file at a time, if that actually worked. I have to look into that. So that was the overview of the basic startup logic. So coming into the program from either the workbench or from the CLI, and then doing the basic command line processing and picking up the second parameter when you come from the workbench side, and then you end up in the main entry point, which is Command X. So you could actually, you can use this to study how Amiga startup is treated in assembler. And I mean, basically the flow, I mean, it's identical if you write the code in C, so you just replace the assembler code with C, so not much thing. But the reason I did this is that when it comes, specifically when it comes to the assembler, usually you find lots of examples of either an application, or you find out for the startup logic, or when you find an application example, and it's like there's not enough comments to really understand what the heck's going on. So I thought I'd make a very concise example here, and a well-documented example, so that you can actually understand what's going on. And then of course if you take this and you embed it in your own application, you just throw away the comments you think you don't need. But this will enable you to create a simple Amiga OS application that can be both started from the CLI or from the workbench, and you will know which is which. And then it also has basic command line processing as an example. So this is a very good starting point for anybody who wants to start assembly programming from the basics in Amiga. So hope you stuck with me and enjoyed this one, and more to follow.